Hello and welcome to another tutorial in the Handmade Data Structures in C tutorial series. I'll be your host. I'm Christopher, the sometime editor and director of the previous Handmade Data Structures tutorial series, and today we're going to be covering linked lists. Before I start, it would probably be a good idea to explain the difference between linked lists and other kinds of lists. So, in computer science, there are three general types of lists that you'll come across most often. The first one is arrays. With an array, you generally have it built into every language, especially C. C's only type of built-in list is an array. An array can hold multiple things, as all lists should, but the thing about arrays is that they can only hold a certain amount, and they have to have a consistent type. So, with an array, in C and in other languages, what you do is you specify the number of things that you want it to be able to hold and the type of the things that it's holding. The reason you have to do this is because arrays are represented simply as pointers into a place in memory. So the number that you specify with an array is the offset that you can add to the pointer. An array also needs a type, and a consistent type, because the offset isn't necessarily in bytes. It has to be in multiples of bytes, because an array lays out all the things that you put in it right next to each other. So if I had an array with an int and a float in it, those have different sizes, so if I wanted to access something after the float, I wouldn't know what the offset should be unless I had a list of every single type in the array. Instead, how arrays work is, again, they have a single type. So if I have an array of ints, well, ints are 16 bits, or 32 bits, or 64. Let's just say 16 for the case of explaining. And so if I access the array index 4, it's going to do 4 multiplied by 16 and then add that to the pointer to the beginning of the array. This assumes, of course, that the array has a size greater than or equal to 4. Also, arrays need to have a size so that the compiler or the operating system knows how much memory to allocate. Vectors are the second type of list that you can get in computer science. Vectors are like arrays in that they represent their contents as a single continuous piece of memory. However, unlike arrays, vectors can grow to different sizes. In addition, vectors can grow to any size you want, as long as you have enough memory to store it. How that works, as we explained in the previous tutorial video series, is that vectors have a load factor. A side effect of this is that vectors can sometimes take up more memory than they need, but generally they're more space efficient for things that need to grow. The third type of list that you'll come across in computer science is, of course, the linked list. The thing about linked lists is that they're not represented as a continuous block of memory like arrays or vectors. Instead, they're represented as several small chunks of memory, called nodes, that have pointers to the node that comes after them and the node that comes before them. This way, they're more like a bead necklace than a ruler or a stick. So the benefits that a linked list can give you is that linked lists can not only have multiple types of data, because you can just store any type you want in the node, because you don't have to have a consistent offset. They also are very quick for inserting and deleting, because all you need to do to insert something is put it between two existing nodes and update where the pointers are pointing to. And to delete something, you just do the inverse of that. You take something out from between two nodes and update what the two nodes pointers are pointing to. You don't need to move anything around or free anything, and for allocation purposes, linked lists only have just as much memory as they need at any given time. The downside to linked lists is that, unlike vectors and arrays, where if you want something you can just immediately jump to that offset and immediately have what you want, with linked lists you have to traverse the linked list one by one, going down from parent to child of that child to child of that child's child, using the pointers to the next node, or from child to parent to parent to parent, using pointers to the previous node. So, now that I've explained what all these things are and what the differences are, I'm, of course, going to explain how to make a linked list. Let's get started. For this video, I've prepared a test in main.c. So in main.c we have int main, which is the function that C uses to actually run a compiled program. We include linkedList.h, which is the header file that will contain the list of structs, types, and functions that we're actually going to provide to external users of our linked list. Then inside the main function, it performs a few tests. It creates a first node and then pushes a few nodes onto that node, therefore creating a larger linked list of 100 nodes. Then it prints them all out. Then it finds a specific one using a utility function that I have defined. Then it removes that specific item, and then it finds the item at that same index to check that the whole list has adjusted to the removing of that one item, and then it frees. So let's get started. First, I should explain a little bit more about headers in C. So in C, generally what you have is a main C file, although it doesn't have to be called main, that contains the main function that does actually have to be called main. That's where the operating system knows where to actually start executing your program. You can define all sorts of things in the main C file, the file that contains the main function, but you can also include a header file. So when you do that, what C essentially does, the C compiler, is it goes and finds that header file and looks at the types and functions that that header file has in it. And then it finds the source file that has the same name as the header file, except .c instead of .h, and copies the types and structs and functions listed in the header file from the implementation file into the place where the header file was included. So for instance, if I were to make a function foo, right, in the header file, and I were to implement it in the linkedList.c file, right, and then I include it in main.c using include linkedList.h, the including file, the file that goes and includes that, would then actually get a copy of the foo function that it could use. But if I implemented functions in linkedList.c that I didn't list in linkedList.h, the main file would not be able to use them. Okay, so since the header file determines what external programs we'll be able to use from our program, we're going to want to figure out what our interface looks like and put that in the header file. So the first thing that we need to define is a node, right? Because a linked list is just however many nodes that contain the data and have pointers to each other. So let's start with that. So first we're going to need a pointer to the previous node, and a pointer to the next node, and a pointer to data. Now, as we discussed in the previous video, or videos on vectors, void pointers are a really good way of taking data that doesn't have a specific type. Otherwise, I'd have to specify a type, like int or char. And if I did that, then the linked list would only be able to be used with ints or strings, and we'd have to make new linked lists for every new type that we wanted to use. However, C has a specific way around this. So in C, void means the absence of a type. But a pointer has to actually point something. It can't point to nothing. Well, it can point to garbage, but it can't actually point to an empty space. It can't point to void. So instead, when we say a pointer to void, what we actually mean is a pointer to something that doesn't have a type, which means that can be any type. The danger with void pointers is that it leaves it up to the user of the library to keep track of what that type is, but that isn't too hard, especially in this case. Now, you'll notice here that when we actually reference this type, we have to put the struct keyword in front of it. That's not very ergonomic, but we can't help it when we're inside the struct, because the struct only has access to itself, and types defined before, not anything after it. However, in order for external people to be able to use our program more easily, we can do a type def. In C, a type def defines an alias, an alternate name, a synonym for a specific type. So in this case, we're going to give struct LLNode an alternate name of LLNode_T. This way, when we define our linked list new node function, we can actually say LLNode_T instead of struct LLNode. Okay, so what sorts of arguments does linked list new node have to have? In order to create a new node, right, we need arguments that refer to each of the properties in the struct, right? Because structs are just a chunk of memory where each property points to a certain value, right? So structs combine a bunch of different variables, essentially. So we know we're not going to need a void pointer to data, and we know we're going to need a pointer to previous and next, which, by the way, can be null if you don't know what the location should be. Now, but there's one more thing that we're going to need. See, if we did this, the users of our library would have to allocate memory manually for themselves, and then when they free our linked list, they'd have to remember to free all the data that they made themselves. The problem with this is that they'd have to somehow store the data that they gave to our linked list somewhere else. And what's going to happen is that they're going to need like an array and a linked list, which sort of defeats the purpose of having a linked list. So instead, we're going to use Mem Copy. What that does is it copies all the bytes, a certain amount of bytes, from a source to a destination. So in order to actually do a Mem Copy, we need to know how many bytes to copy. In this case, a size t len. Now, in order to actually use the size t type, you actually need to include string.h. What size t is essentially an unsigned integer. Now, the problem with directly using unsigned integer in C is that unsigned integer can actually be different sizes depending on what machine you're on or what operating system you're using. So if we want something consistent that's always the correct size, size t is always the size that you need to address memory. And since that's what we're doing, that's what we can use. And you might think that we just start directly writing code in headers. However, that's actually not the case. Headers just list the type signature, the return type, and the argument types of the functions that it makes public. Okay, so the next function we're going to need is some way to actually add things to the linked list. We're going to call that linked list push. Now, you could have linked list actually take a new node, but again, we'd have the same problem where people would have to manually manage and keep track of the memory that's in the linked list, even when it's in the linked list. Instead, I'm going to have it pass in a void pointer to data, a size t len, and last but not least, or actually first and not least, a pointer to the node that we're actually adding this new node onto the end of. We'll call it head. Okay, that's done. So the next thing we're going to need is the linked list find ith from. Now, this is not a necessary part of implementing a linked list, but it's really nice to have, especially for testing. Notice that the index is a size t because, again, we're indexing the memory. The next thing we're going to need after that is a way to remove an element from the linked list. So linked list remove, and we just give it the item. Because remember, in a linked list, it's separate nodes, little chunks of memory, specifically chunks of memory that are structs, that have a pointer to the previous and next node. So if you want to remove a node from a linked list, all you need is that one node because it has access to the adjacent nodes in the linked list, so it can modify them when it needs to. And then, final thing we're going to need is a way to clean up the memory for the linked list. And obviously that needs a reference to the node. Preferably, of course, a reference to the very first node in the linked list. Okay. So now that we know what we're going to need to implement, let's copy all this into linkedlist.c. Now, the first thing before we paste all this in is we're going to actually need to include linkedlist.h. This is partly how the C compiler understands that linkedlist.c actually implements the stuff listed in linkedlist.h. Alright, so let's paste this in. Now, those semicolons are actually not correct syntax anymore, because in a .c file it expects implementation, not just declaration. So, let's put in some fancy curly braces. Alright. So, how are we going to implement linked list new node? That's a good question. So, whenever you create a new struct, normally, and in fact almost every time, what you do is you have to allocate memory. This is because when you create an array or a string or a number, the C compiler can push it onto the stack, which is sort of another way of managing memory in C. However, that's because those are things that have a fixed size, that don't change over time, and that C kind of understands and knows what the size is. And those values tend to be values that are more obvious when to free. However, for structs and things like that, for memory that can either change or change size or that you define, you're going to need to allocate some memory on the heap, which is where the operating system actually stores more nebulous things. Now with the heap, the compiler can't figure out when to get rid of that memory for you, so you have to keep track of it. That's why we have linked list.free. So how do you get that memory? Well, you use a function called malloc. So let's create a node named new, right, because it's a new node, and malloc. So the argument that malloc takes is the number of bytes that you actually need from the operating system. If the operating system is successful in allocating that number of bytes, it will return a pointer to you. So this is what we're doing. So let's put in, now we can't just put in len, because len is for the data, not for the actual struct. What we need to do is get the size in bytes of our struct. Alright, now in order to actually use malloc, we actually need to include stdlib.h. Notice that the angle brackets mean you're including something that the operating system knows about, that's part of your system installation, whereas the double quotes include something that is local or specific to your program. Okay, now, first thing we're going to do on this new is set the next attribute to the argument next up here. And the next thing, if you'll pardon the pun, we'll do is set the previous. Now, data is a little more complicated. As I just mentioned a few seconds ago, for data, we actually need to, again, malloc some memory. The reason being, we're copying the data from what the person passes in to somewhere in our struct. The struct doesn't know the size because it's a void pointer, so we actually need to get a pointer to enough memory to store the stuff that we're copying. So we need to malloc len amount of bytes. Then we do a mem copy, which the argument order is destination, and then source, and then amount. Then, when we're done, we return the new node. Alright. So, now that we've implemented linked list to new node, linked list push is a lot simpler. How that works is, first we make a new node, of course. Right? And we pass in the data and the length. Now, here comes the interesting part. So, for push, we take a node and we want to add a new node right after that node in the list. So, since the new node is right after the node that was passed in, it's the new node's previous node pointer is going to be the head, the node that was passed in. The new node's next pointer is actually going to be head's pointer to whatever used to be next. That's because there could have been another node that was already after head, and we want to push this new node in between them. So now the new node has a pointer to its parent, which is the node that's being inserted after, and to its child, which is the node that should go after it, now that it's in there. Now we're going to need to set head's child reference to the new node, therefore overwriting whatever was in head next, but don't worry, we've just saved it in the new node. Then, for convenience, we can return new. Or actually, don't necessarily have to return anything, but how about the next node? That way you can repeatedly call linked list.push. Actually, returning new makes more sense. Okay, so now we have linked list to find ith from. This is a particularly good example of actually understanding the structure of what a linked list is. So we're going to iterate, and instead of an integer, we're using a size t because we want to directly compare it to the index. What this will do is it'll execute this loop index number of times, meaning that when we do this, we're going to get the next node after the current node index number of times, meaning we're going to go from head to the next node, and then the next node, and the next node after that, until where we are index number of nodes away from the original node that was passed in. And then we just return the node that we got to. Simple. Now, linked list.remove is a little more confusing because, like push, it has to do some adjusting of what the pointers were. Unlike push, there's more pointers to adjust. So how this is going to work is we're going to take the parent of the node passed in and set its pointer to its child to the child of the item that was passed in. This way, when we're going down the linked list, so from parent to child of that child, child of that child, we skip the node that we're removing. Now, we essentially have to do the opposite. We set item's child's pointer to its parent to item's parent, so that when we're going from the bottom of the list up, once again, we skip item. Then, since we own the memory that item represents, we can go ahead and free the data in item and free the item itself. Again, if we had decided to not use Mem Copy, this wouldn't have been possible. Also, since we're freeing this, we actually don't want to return anything. There we go. Okay. And finally, we have the free function. This is the capstone of this entire setup. What the free function will do is it goes through from head to the very last node. When head is null, right, will be at the last node. And if it isn't null, what it does is it frees head. The problem with this, of course, is we're not actually iterating. We're not getting to the next node. Now you might think we could do this, right? Free head, and then go to the next node after head. Unfortunately, that doesn't work because we've just freed head. We don't know what the next node was going to be. So instead, we just need to set an intermediate variable called next and set it to what head's next pointer was going to be. We don't have to worry about freeing next because it's going to be freed in the very next iteration of the loop. Okay. Now that we've finished that, we can go ahead and give it a shot. So I'm going to switch back to main.c. Now, I've actually set up a nice little compilation environment that lets me type make to build the program, and then I'm going to use valgrind to actually run the program. Now that I've just checked to make sure that hold on. See, this is why I like valgrind. So, I've made a mistake, and it's actually a good time to explain what the mistake was. So, valgrind is a tool that runs your C program and keeps track of how much memory was being used at the beginning, at the end, and during your program's running. This is great because C doesn't manage or keep track of memory for you, unlike Python or other garbage collected languages, and also unlike Rust, which essentially has Valgrind built right in, so it won't even let you compile if something like Valgrind will give you an error. You'll see you can look up the exact command, but essentially what I'm telling you here is to check for memory leaks, and that I only really want it to check on memory. So you can see here, keep summary, and you set exit 396 bytes. That's not good, it should be 0. This means that we're leaving 396 bytes of stuff in use when the program closes. If you look here, it'll say that we allocated 201 things and only freed 102 of them. That's almost exactly half. Why is that? Well, if you'll recall, when we did linked list remove, we separately had to free the item data and the item itself. This is because we had to allocate memory inside the struct, inside data, to store the actual value in the linked list. But then we also had to free the node itself, item, because we had to allocate memory to actually store any of those pointers. You notice here, however, I forgot to free the data. Now if I fix that and compile with make and run Valgrind again, you'll see it doesn't scream at me anymore. 0 bytes, 201 allocs, 201 frees. Alright, so let's go over the output here. So essentially what we did was we created the very first node with a value of 1, and then from values 2 to 100, so starting at 1 and going to 99, but adding 1 to that value of the index when we actually push it onto the linked list, we add 100 values. This way we have a linked list that contains the values from 1 to 100. Then we get the 20th item. If we check here, sure enough, the 20th item, which comes at index 20 and is therefore stored as 21. Then, as you'll see here, we remove that item. Then we check in the list what the new 20th item is. If it worked correctly, the rest of the item would be removed and we would just skip it. So when iterating down the linked list to find the 20th index, it would hit 22. And sure enough, it did. Okay, now that we're done, the code will be posted with a few cleanups and further information, as well as my full build system in case you want to use it, at github.com/ChristopherDumas/clinked-list. No punctuation or capitalization. I hope you enjoyed this video. I hope it was helpful. Please tune in for more of the tutorial series, Handmade Data Structures in C. And please also look out for a 2-part series I intend to make on C, including the C primer and C memory types and header files. Thank you for watching, and see you next time.